Okay, so hi everyone. Yeah, I'm Ed, and I'm studying at Bristol with Jonathan, and I'm going to talk about resuspension today. And this is also a project that's partly supervised with some people at DSTL as well. And I'm mainly going to talk about the 3D printed wind tunnel bit of this, but also a bit about how morphology affects particle resuspension. So. Okay, so I guess why do we care at all about resuspension? So we know it's a kind of phenomenon that is happening like continuously in the environment, mainly because forces that detach particles from the ground are stuff like wind, which we always have, but also any kind of movement, cleaning, stuff like that. So we're kind of always constantly surrounded by a slightly higher concentration of aerosols due to particle resuspension. But currently we don't really include them in aerosol dispersion models as like a source of aerosol in surroundings. That's basically because we've got all these factors here. Oh, sorry. All these factors here that make the kind of whole thing a bit more complex, and we kind of need to take it back down to basics and understand each of these different factors in turn. So how people have gone about looking at resuspension in the past. So I'm going to start with the right-hand side. So we have like empirical models. So here is a slightly terrifying robot baby. So these kind of models take a very specific scenario and try and look at it in quite a lot of detail. So here the robot baby is going to crawl across different kinds of rug. And these are good models for if you're always looking at that scenario, but maybe they're not very applicable if you need to use them in any other situation. So the kind of different way of looking at it is to start from the very basics of like the most ideal situations. This is where mechanistic models come in. You kind of build these up from kind of bottom level physics and you add complexity as you go along. So here we have a spherical particle, and to add a bit more real world complexity, they've put hemispherical lumps on the surface. And so if you continue to stepwise increase the complexity of these models, hopefully at some point you'll have something that is widely applicable to lots of different scenarios. And that's kind of where this research comes in. So this also requires some kind of experimental research, either to inform what you're going to do next or to validate the model once it's been made. So at Bristol, we thought maybe we could do this because we have lots of instruments that can dry particles in very controlled conditions. And what you get is particles of very reproducible size, shape, particles that we know quite a lot of information about. So this here is the falling droplet column, which Dan Hardy built a couple of years ago. So here you have particles that enter at the top of the column, they dry as they fall, and the particles that deposit are very reproducible. So if we had something that could then resuspend those particles, you could have quite controlled experiments and look at particle morphology and other factors that way. So most of my time so far has been focused on building this wind tunnel. So when we set out, because we didn't have a wind tunnel in Bristol, well, at least in the chemistry department, we wanted something that we could hopefully build quite quickly, quite cheaply, and also not take up too much space in the lab. And once we built it, we thought, oh, maybe other people might want to use this as well. It could accelerate that, looking at all these different factors in resuspension research. So what you kind of need for this to actually work is you want your wind tunnel to be able to show the typical resuspension characteristics. So stuff like large particles are more likely to resuspend than your smallest particles. Generally, you expect when you turn on an airflow, there's going to be an initial rapid release of particles. Those that are weakly adhered to the surface will come off immediately. And as you go on, this will become like a steady, longer term removal due to stuff like turbulent eddies that break the boundary layer and detach the particles from the surface. So you want to kind of verify that those flow conditions are actually taking place. So we actually get this image on the right-hand side. And there's a few other things to make sure you actually have an ideal scenario. So stuff like there's no static effects coming in, there's no collisions, and things like that. So this is a wind tunnel. It's a fairly standard looking wind tunnel. So I'm not going to go through it in too much detail, but we have air coming in here. This is all 3D printed, and it's about 1 meter in length. So we have air coming in at 100 liters per minute through a mass flow controller. It then goes through the settling chamber, and what that does, it laminarizes the flow with like ball bearings and honeycomb lattices, and then you kind of immediately induce turbulence again. And the reason for doing that is so that you can control the turbulence that you're getting. You're not just getting something different every time. And then here's where we actually look at the particles getting removed from the surface. So we do this at about 500 frames per second, so we can actually see some like the particles physically detaching opposed to them being just there 1 second and gone the next. So I do an experiment. So first we were looking at just spherical glass beads. We want to make sure the ideal scenario works. So we disperse them on the surface. We look at between like 60 micrometer and 9 micrometer diameter particles. And this should be a little video of them coming off the surface like that. So we look at that a lot. And then offline, this is the same video with some green circles around the outside. We do some offline data analysis to count those particles and just to kind of take out any particles that are just like debris that just happen to be on the surface at the same time. So that's what I've been doing with glass particles. One of the major challenges that we came up against was particle collisions. So often we see something like this, where even though there's hardly any particles on that surface, they're all getting removed. Both of those particles are removed by collisions, which isn't really a true resuspension event that I currently want to look at. So by kind of going through all the images that we get, we've kind of narrowed in on a surface coverage of particles that actually means you don't get collisions, which is around 1 particle per millimeter squared for your biggest 60 micrometer diameter particles. This isn't very physical, I guess, in terms of the natural environment, but it's what you need to kind of get your ideal scenario for this stage. So it might be something to look at in the future, where these collisions or how important collisions are. And this is the kind of data we get out on this side. So thankfully, the largest particles are removed more easily than the smallest particles, which we expected. And also you see this initial rapid resuspension, and then you get longer term over the next like 20 seconds after that initial airflow, you get more steady, longer term resuspension as well. And so this is hopefully suggesting we do have turbulence in the tunnel. And maybe another qualitative measure of where we have turbulence is stuff like laser sheet imaging. So here, I just put some particles through a laser going down the tunnel and take a look at that. It's more useful when you compare it to when you don't have turbulence. But this is to show what we have. And hopefully at some point we'll have some quantitative analysis of that as well. And so just briefly to talk about particle morphology. In the future, when we actually resuspend particles are more interested in morphologies and spheres, we'll hopefully use something like the FDC to make these particles. This is some work I did with some sugars a little bit ago. So with sugar, as you get this rapid period of evaporation initially, so the sugar kind of ends up mainly on the surface of the particle. That surface locks, and you end up with an internal cavity that starts off with probably some water inside it, and then eventually we'll just have air inside it. And depending on the relative humidity you have for that particle to dry in, you get different rates of buckling. So this is going from 10% relative humidity to 40% relative humidity. And this is maybe an example of how we can deviate from sphericity in quite a controlled manner. So kind of the next main step is to introduce this morphology into the experiment. So one of the things we need to do is build a trap. So Rob talked before about the slabs in Langford. So something like the slabs where you can trap a particle and then at some point deposit it. So with the falling droplet column, particles are already falling. So they may not dry in time before they hit the surface. So if you can indefinitely trap them and then deposit them, that is something that would be very useful. We had a math students who did do this with the slabs in Langford. So it's with salt crystals, which look a bit like this, and then they get removed. So we just don't want to have to keep traveling back and forth to Langford, which is about a 50-minute bus ride with these particles. Yeah, apart from that, thank you for listening, and thank you to Bart.